All right, let us continue with quantum field theory 2. We are at the end of our discussion of path integrals and general path integral methods. And in particular, right now, we are in the middle of a section on path integral manipulations, where I show you that simple tricks applied to the path integral give rise to very general and powerful formulas and relationships between, in particular, green functions, such as Dyson-Schwinger equations and Watt identities. And the last time I wrote 2 examples onto the blackboard, and today we will derive both. And so I will not repeat them, but we will come to them with a full derivation. So let us, however, begin in more general terms, namely with Dyson-Schwinger equations in general. So the condition under which we will derive these general Dyson-Schwinger equations is that the path integral measure is invariant under infinitesimal field transformations in the way we defined it at the end of the last lecture. So we assume now that the measure is invariant. And if the measure is invariant, what you can basically do is you can do a shift of the integration variable and then take the functional derivative with respect to that shift that we called delta phi. So you take a functional derivative with respect to this delta phi of x. Then you will simply see that a path integral over a total derivative must always vanish. And that is the same as we have for normal integrals. If you do a shift of the integration variable and the integration measure and the boundary is invariant under that shift, then it implies that an integral over a total derivative, of course, has to vanish. And if we write that as a formula, as a path integral formula, then that formula would look like this. So the path integral over the appropriate set of fields of any functional total derivative with respect to any field variable, say phi k at some space-time point x, of anything, for example, of this expression, functional of the fields times e to the I times the action. This operation gives 0. And also, just to recap, this e to the I times the action is the usual integrand of the path integral, which generates the dynamics of the theory. And here we insert also some additional functional of the fields, which would normally be a product of field operators in order to generate a Green's function. Okay, so this is then the simple statement. And
طبعا في نظريتي هي صحيح 0، لكن طبعا في الانتراكشنز ليست بزيرو، فبالتالي أي تحرك في الفيلد يعطينا نتيجة وليست بزيرو. هذا حسب نظريتي، وليس فقط في الفيلد، يعني الشفت ليس يكون في الفيلد فقط، وإنما حتى في الفضاء أيضا لا يعطينا زيرو. وهذا ما يجعل كتاب الحلقة 54 فعال وصحيح، ويعني له دلالاته يعني. فهذا الديريفيتيف هو هذا الشفت في وضع في التفاعل ليس صفرا، لكن بعد الخروج من وسط التفاعل، يعني الخروج من التفاعل إلى الفري بارتيكل فري لاجرانج أو إلى الفضاء رباعي الأبعاد، فإن القيمة تكون صفرا كما ذكروا.
This is basically already a Dyson-Schwinger equation, but let's bring it into a form which is more explicit. namely into a form for concrete green functions, in other words, time-ordered expectation values of some field operators. So for concrete green functions, we can write down the following, the same expression, but now let's really insert for the functional here our product of fields and see what happens. And so let's put now here an argument y to be more explicit, and here let's put the following, a certain string of field operators, and to make it a little bit more explicit, or let's say non-confusing, let me write the following, phi I1 of x1 up to phi in of xn times e to the I times the action. And so why these indices? In general, we have a lot of different field operators, and we call them phi 1, phi 2, phi 3, and that might stand for the photon field, the electron field, the Higgs field, and so on. And here there is just some set of fields, like the photon field, the Higgs field, at some different space-time points, and therefore I do not want to label them here in this case with phi 1, phi 2, because it's any set of field operators that you might choose, and you take a derivative with respect to one of them of the entire integrand, and then we know that this path integral here must vanish because the measure is invariant. And now let us apply the functional derivative to that expression. If we apply the functional derivative to that expression, we get, of course, a product rule. We have here a product of some field operators. Some of them might be different from that one, then the functional derivative gives 0, and some of them might be the same as this one, and then the functional derivative gives a delta function between the arguments. And then we have the functional derivative of the exponential. So let's write this. So from the first term, we get a sum over all these different field operators. Let's say a sum over, how do we call it, L equal 1 to n, the number of those fields. And for any term, we get, how do we write it, a Kronecker delta I of the appropriate index times a delta function of the arguments y minus xil. That comes from the functional derivative of the appropriate field operator, and then all the other field operators here are unaffected. So we have phi I1 up to phi in, but the one field operator with the index phi il or phi k is missing. Because we took the derivative of it, and the result is this delta function. And then all of that is multiplied with e to the I times the action. So this is the functional derivative of each individual phi, and then we have the extra term from the product rule where we take the functional derivative of the exponential. So we have plus, then first of all the field operators in the front, they are unaffected, and the functional derivative of the exponential gives, of course, the same exponential times the inner derivative, and the inner derivative is I times the functional derivative of the action with respect to phi k, and we just write it as it is, functional derivative of the action with respect to phi k at space-time point y. That is the result. Okay, and so here we have now an explicit path integral formula of a path integral over a sum of terms, and the total result gives 0. And that is the Dyson-Schwinger equation. That is the Dyson-Schwinger equation, and we can write it in terms of operator language, just to translate the expression into operators, to visualize maybe a little bit more what we have here, but that's already the Dyson-Schwinger equation which we were looking for. But let's translate it into operators, then it becomes a little bit more compact. So the first line corresponds to what? L equal 1 to n. So the first line is a path integral over the usual exponential times a set of field operators where one field operator is missing and replaced by the delta function. So this path integral generally up to a normalization, it generates a green function of those field operators without phi k. So this is a green function with n minus 1 field operators. So let's write it down. So it would be up to normalization, this green function of a time-ordered product of these operators, phi I1 up to phi In without phi k times the delta function times Kronecker delta k il delta function of y minus x il. Okay, so such a set of green function. And the second line, what is the second line? The second line, first of all, times I. Then we have here a path integral over this set of field operators times something else here on the path integral level. This is of course a functional of the fields. It might contain a product of fields. And in QED we will see an example of that. So this is some product of field operators which arises from the derivative of the action with respect to a field. And so we have a green function of a set of elementary fields times a composite operator, this sort of green function. So let's write it down. Time-ordered product of all these field operators, phi I1 up to phi In, times this composite operator which arises from the functional derivative with respect to phi k at position y, interpreted as a composite operator. That's the Dyson-Schwinger equation. So why is this interesting, and what is the particular feature you should keep in mind about this equation? The particular feature is that we have here this object, the functional derivative of the action with respect to a field. What normally is the functional derivative of the action with respect to a field? It gives you the how's it called? Euler-Lagrange equation of motion. The Euler-Lagrange equation of motion, which would be zero according to the classical equations of motion. So what we have here is a composite operator, which, if you look at it at the classical theory, satisfies an equation of motion. So this object would be zero in the classical theory if the equation of motion is satisfied. So what you are asking here is, what is the result of an operator expression in the quantum theory which would vanish according to the classical equations of motions? What happens if I take this operator expression and evaluate matrix elements of it? The Dyson-Schwinger equation seems to tell you that in the quantum theory this operator does not vanish. It doesn't vanish as an operator, and not even does it vanish if you evaluate matrix elements of it, because here you have some matrix elements of this operator, and the result of that matrix element apparently is not zero, but it is zero up to those green functions here in the first line. So the Dyson-Schwinger equation tells you the fate of equations of motions in the quantum theory. That is the interpretation. But let's write it down. So this thing here is an insertion of an operator which would vanish according to the classical equations of motion. But it doesn't vanish in the full quantum theory because of the time ordering here. So again, the whole thing depends a little bit on this trick that the path integral green function and the path integral time ordering which we use here, this is this path integral time ordering, which always commutes with time derivatives, and therefore the time derivatives which stand here, they by construction commute with the time ordering here, and therefore this creates certain delta functions from these derivatives, and those delta functions correspond to the green functions in the first line. But time derivative commutes with.
طبعا في نظريتي الدلتا بالنسبة للاجرانج أو الأكشن لا يساوي زيرو بالنسبة للاجرانج على أول مشتقة اللاجرانج الفاريشن اوف لاجرانج على بالنسبة للفاي اللي بتعطينا equation of motion لا يساوي زيرو، وهذا واضح في كتاب الحلقة 54 حيث ذكرت أنه equation of motion إما أن يعطينا موجة متضخمة مع مرور الوقت أو مع مرور المسافة، يعني من داخل التفاعل وسط التفاعل موجة تتضخم، أو موجة ناقصة من نهاية التفاعل لوسط التفاعل، لكن احنا دائما نتكلم من وسط التفاعل إلى نهاية التفاعل، فهذه الموجة تكون موجة متضخمة. نعم تكون موجة متضخمة. طيب وبعد بذلك نجد أن هذا الحد لا يساوي زيرو، هذا الحد لا يساوي زيرو، وبالتالي يكون هذا الحد مساويا إذا ودينا بالطرف الآخر لعلامة التساوي يكون مساوي لذلك الحد. فبالتالي الحد الأول، هذا الحد الأول يعطينا الذي يعطينا دالة جرين. طبعا قلنا دالة جرين يجب أن تكون أقل من الزيرو من الواحد وأكبر من الزيرو، ويساوي هذا الحد. هذا الحد أيضا يجب أن يكون أقل من الواحد وأكبر من الزيرو، لكن لا يساوي زيرو، لا يساوي زيرو. بالتالي تعطينا موجة يعني ممكن أن نحول طبعا البعض نحوله بالطرف الآخر، نقسم كل الأطراف على المعامل لهذه الدالة، تكون دالة جرين على هذا المعامل، وهذا المعامل يعتبر دالة جرين، يعني معادلة فوق هي ليست دالة جرين وإنما الشفت في دالة جرين على المعاملة تحت هي دالة جرين بالكامل. ربما يكون ذلك بإشارة سالب، بإشارة سالب، وهي معادلة ليست صفرية، تعطينا إما معادلة متضخمة أو موجة متضخمة أو موجة متقهقرة تبع الإشارة السالب أو تبع الإشارة الأعلى.
This path integral effective time ordering, therefore result does not vanish. But you see, the result actually does vanish if all the space-time arguments of the field operators are different. The result only is non-zero at singular points where space-time arguments of the field operators coincide, because then the time ordering singularities matter, and they differ in the operator formalism and in the path integral formalism, and in the path integral formalism the time ordering has this property that it commutes by construction with time derivatives, and that generates here this non-zero result. So I also want to point out that we have already seen a special case in the free theory, which was our section 172, where we basically derived that the free propagator, the two-point function in the free theory, is always the inverse of the differential operator. And that is exactly the same kind of equation, just applied to a two-point function and to the free theory, where then this derivative would be linear in the field and it would correspond to the differential operator applied to the field. So this Dyson-Schwinger equation, if you plug in the free theory, reproduces exactly our section 172. Here is the general Dyson-Schwinger equation. And as a side remark, an interesting side remark, this can be used as a starting point to build up quantum field theory entirely, and also perturbation theory. And there is one textbook which does exactly that. That is the textbook by Tom Banks. So I can recommend you to look into this book. In a way, this would be a third way to start quantum field theory. The standard way, which we did last semester, would be using operators. A second standard way would be using path integrals, and that, in a sense, can be regarded as a third way to start quantum field theory, because he basically gives a motivation in this section 1, and then section 2 or 3 is immediately this, and then it goes on. Okay, so this is the Dyson-Schwinger equations, the fate of equations of motion in green functions and in the quantum theory. And so let us now look at a special case of that for a QED, which will reproduce the equation that we had on the blackboard last time. So an example, Dyson-Schwinger equation in QED. I claim the following, and actually there was a misprint unfortunately on the blackboard at the last time. Namely, we have here all higher order diagrams. And unfortunately on the blackboard I wrote all diagrams, but it's only all higher order diagrams, and the result is this. Namely, you can write this as a 3-level photon propagator times a 3-level vertex times 3-level electron propagators, and then all Feynman diagrams connecting the 2 electron lines and a photon. So this is a green function, a 3-point green function, which is then connected with a 3-level Feynman diagram to form a photon self-energy. And here on the left we have the full 2-point function for the photon, except for the 3-level Feynman diagram. So this is a Dyson-Schwinger equation which corresponds exactly to that structure. It's an exact relation between different green functions. And so this is just a very basic example, and let me just mention that more detailed versions and more detailed statements are also possible. But we will not do this here today, since the point is just to give you an illustration and a glimpse of what Dyson-Schwinger equations are, how they can be derived and how they can look like, and then one might go on in case it's necessary. Okay, so let's prove this equation. So we prove it exactly in the style that we have indicated at the top. It's a special case of what we did at the top, but now applied concretely to QED and to a concrete string of particular field operators which we take functional derivatives of. So what do we need to start with in order to obtain this particular equation? We start from the following, namely we have here the QED path integral. Then we take the functional derivative with respect to a photon field at point y, a nu at y, of another photon field, a mu at x, and e to the I times the QED action. So this is the starting point of a Dyson-Schwinger equation, namely you take any integrand and take the functional derivative of it with respect to something, and you get 0. Okay. Now, in order to evaluate it, let us recall that the QED Lagrangian can be written in this way, namely 1/2 times a rho, then a differential operator d rho sigma a sigma. So this is the free part of the photon Lagrangian, plus a rho times j rho, where j rho is this, minus eq psi bar gamma rho psi. So this is the current the photon couples to, and the Lagrangian also contains the free part for the electron, but let's ignore that, we don't need it for this derivation. Then we can evaluate this functional derivative here. If we do it, what do we obtain? We obtain on the one hand a functional derivative of a mu with respect to a nu. That of course gives a delta function, and in this case it's a delta function between x and y, and a metric g nu mu between the two Lorentz indices. So we get immediately this delta of x minus y times g mu nu. And then we get the path integral over just e to the I times the action, which gives a normalization factor, and I will immediately drop this normalization factor from the equation. Then the second term gives us the following, namely a mu times the functional derivative of e to the I times the action, which gives e to the I times the action times the inner derivative, which is this equation of motion for a mu. So we will now get a green function, like here at the top, a green function which involves the equation of motion for a mu. So let's write it down. I times, here green function, a mu of x times now the equation of motion for a mu. What is the equation of motion for a mu using this formulation of the Lagrangian? Of course, simply differential operator d rho sigma times a sigma, but with which index? With an open index nu. d nu sigma times a sigma at position y. Then plus the current plus j nu also at position y. Okay, and I will drop here now these arguments with the time ordering and the omega expectation value and so on, just to keep the notation short. And here again I've dropped the normalization factor. It is the same normalization factor that I also dropped here. So this is immediately the equation corresponding also to the box at the top. So now, since we use the path integral time ordering here, we can pull out the derivative operator out of the green function, and then we get here the following. This remains the same, plus I, and then we have here the following derivative operator, d nu sigma, differential operator applied onto this green function here, a mu of x, a sigma of y, and this derivative operator acts with respect to the variable y. And then we have another green function plus I times the green function, and here let's plug in the current. So the current contains a number valued prefactor minus I eq times the following green function, namely of a mu of x, and then psi bar gamma mu psi at position y. Okay, and now we have three terms. The first term is simply a delta. The second term is a full two-point function of the photon, the full photon self-energy. This corresponds to exactly all diagrams, including tree-level and all higher-order diagrams, but the differential operator is applied onto it. And then this already corresponds to that, because this is a green function here where we have psi bar gamma nu psi. That corresponds exactly to this vertex, times also minus I eq, which is exactly the usual Feynman rule from ordinary QED for this vertex. And then a green function connecting this to a mu. So this is completely that Feynman diagram here, except for the external photon line over there. Okay, so mapping once again, this almost corresponds to this. What is missing is this tree-level photon line. This corresponds to the left-hand side, but the differential operator is applied onto it, and this is something else. So let's massage it a little bit, but not much. So we know that the differential operator is the inverse of the tree-level photon propagator. So I times this differential operator, d nu sigma, times such a tree-level photon propagator, sigma rho, that is minus a delta function, g nu rho delta x minus y, with the appropriate arguments. The tree-level propagator is the inverse of the differential operator times I. So that is one thing that we know, and so in that sense we can eliminate the delta function in terms of this, and then we can also multiply the whole equation. We do first of all a Fourier transformation of the whole equation, then everything becomes momentum space valued. And if we have momentum space values, then the differential operator simply becomes a polynomial in the momentum. So we can multiply with the inverse of that differential operator, which is the tree-level propagator in momentum space. So we multiply the equation with the tree-level photon propagator on both sides of the equation. And what do we then get? Then we get exactly the equation in the box. Let's just write it down. Namely, we then obtain the following. If we multiply with the tree-level photon propagator, here this cancels. That is the inverse of the tree-level photon propagator times minus 1. So we can bring this to the left-hand side of the equation. Then we have this green function, a mu, a sigma, Fourier transformed on the left-hand side of the equation, is equal to this one multiplied with a tree-level photon propagator. Of course, Fourier transformed. Then plus that, which is, as we already said, this green function without the photon propagator, and now we multiply it with the photon propagator, so now it's this thing including the photon propagator. And then we have it as claimed. So that is the derivation.
طبعا هنا المعادلة طبعا ليست صفرية. أنا أحاول أن أقارن بين هذه المعادلة بين نظريتي ومعادلتي في كتابي الحلقة 54. الحد الأول يمثل الجرين فانكشن اللي هو الهاير جرين فانكشن اللي هي الدائرة الكبيرة هذه higher green function of all diagrams. الحد الثاني أحدهما يمثل البروباجيتور المتصل بالإلكترون، والحد الثالث يمثل الجرين فانكشن هكذا. طيب هنا ماذا يحدث إذا زادت الحد شمال علامة التساوي؟ طبعا شمال علامة التساوي هو الجرين فانكشن لكن معكوسة، لأنه هي فورير ترانسفورمد. فورير ترانسفورمد يعني معكوسة، ومعكوسة يعني تعتبر مطرودة من التفاعل. طيب إذا زادت طبعا ستكون نتيجة من شيء معين، نتيجة لزيادة. هي إذا زادت تكون نتيجة لزيادة ضغط التفاعل. طبعا إذا زادت يزيد الحد يمين علامة تساوي، وخصوصا الحد الثاني الذي يمثل بالجرين فانكشن هذا. طيب أين التيار؟ طبعا هذه الجرين فانكشن معها التيار اللي هو التيار يخبرنا من الجاما وجاما نوت والساي بار. هذا هو التيار مضروب في اي اي كيو. هنا يخبرنا هذا أن إذا زاد الحد شمال علامة تساوي يزيد الحد يمين علامة تساوي مباشرة. إذا فرضنا الجرين فانكشن شمال علامة التساوي تعطينا مثلا الطاقة متكثفة في التفاعل مثلا، بالتالي نجد أن يمين علامة التساوي هذه هو عبارة عن الطاقة المطرودة من التفاعل أو التيار المطرود من التفاعل، فإنه يزيد هذا التيار. هذا طبعا تتفق مع نظريتي. وأيضا يزيد البروباجيتور. هذا البروباجيتور موجود هنا في النص، والذي يمثل على ما أظن أحد الخطوط هنا، أو ربما الخط الذي يرتبط ب جرين فانكشن الدائرة الكبيرة. عموما أنا أحاول أن أجعل المعادلة ليست صفرية، أو يمكن نفعل شيء آخر وهو أن نحسب الاشتقاق. في حالة كيو اف تي الاشتقاق بالنسبة للتيار يساوي زيرو، لأن التيار ثابت. في نظرية أن الاشتقاق لا يساوي زيرو، وإنما يعطينا الاختلاف في الكتل التي تظهر في التيار، اختلاف الكتل التي تظهر في التيار. وهذا واضح إذا عملنا مشتقة بالنسبة لشمال علامة التساوي، نعمل مشتقة لجميع الحدود الأخرى. فهنا هذه اليمين علامة تساوي هذه تعطينا التيار. هذه المعادلة تعطينا التيار. هذه المعادلة تعطينا التيار. وهذه المعادلة الدلتا اكس ناقص واي مضروبة في جي ميو، هذا هو يعطينا الفورير ترانسفورم للبروباجيتور، الخط الصغير ده. فأيضا يكون له مشتقة، وننظر إلى المشتقة بتاعته. المشتقة بتاعته لن تكون في الدلتا معروفة، هي إما 1 وإما 0 في ميكانيكا الكم، لكن المشتقة ستصل إلى ماذا؟ ستصل إلى جي ميو نيو. ونحن نعلم من الفيديو السابق أن جي ميو نيو ليس ثابتة، وإنما تتغير بتغير الكتلة. المعادلة الشهيرة اللي هو دي ار على دي ار على دي تي. تعال نشوفها. هذه المعادلة لا ليست هذه، هي طبعا نفس المعادلة لكن أنا لا أريد هذه. طيب لحظة، هذه المعادلة هي نفس المعادلة لكن هنا تحتوي الجي تي تي والجي ار ار. انظر إلى الجي تي تي والجي ار ار ليست بالوحدة واحدة، بينما تساوي هذه المعادلة الكبيرة من النص، ابتداء من النص 1 زائد اللوغاريتم الطبيعي زائد الحد الثاني، وهي دالة في الكتلة ام كابيتال ودالة في نصف القطر ار أو في المسافة ار. إذا جي ميو نيو هي دالة في هذه المعادلة وليست تعتبر الوحدة وليست ثابتة، لا تعتبر الوحدة، وإنما هي دالة في هذه المعادلة. وبالتالي نجد أن البروباجيتور هذا الخط والذي يمثل هنا يمثل بالدلتا 3 اكس ناقص واي مضروب في جي ميو نيو. هذا بروباجيتور أيضا ليس ثابتا وإنما يزيد بزيادة الكتلة ام. لماذا يزيد بزيادة الكتلة ام؟ هذا أمر مهم جدا جدا يجب أن نتطرق إليه. هذه المعادلة تنقسم إلى قسمين. معادلة تخبرنا ماذا يحدث خارج التفاعل، يعني خارج التفاعل خارج الطاقة العالية للتفاعل، ومعادلة تخبرنا ماذا يحدث داخل التفاعل. يعني إذا فرضنا أن التفاعل عبارة عن دائرة، خارج هذه الدائرة تمثل بالمعادلة اللي هو من الواحد زائد اللوغاريتم الطبيعي لسي أس 6 على 16 جي ام تربيع. لماذا؟ لأنه هذا الحد ينقص مع زيادة الكتلة. طيب ماذا عن الحد الثاني اللي هو 2 جي ام على سي تربيع ار؟ هذا الحد يزيد مع زيادة الكتلة، فبالتالي نجد أن الجي تي تي على جي ار ار يزيد بزيادة الكتلة، وهذا ما يمثل داخل التفاعل. داخل التفاعل كلما زادت الكتلة كلما زادت الجي تي تي، والجي تي تي دائما أو الجي ميو نيو دائما ترتبط بالطاقات المطرودة من التفاعل. بالنسبة لميكانيكا الكم ترتبط بالطاقات المطرودة من التفاعل، وهذا يعطينا طاقة عالية مطرودة من التفاعل كما ظاهر في هذا البروباجيتور. اللي هو الدلتا اكس ناقص واي في الجي ميو نيو. هذا طاقة تعتبر طاقة مطرودة من التفاعل، وهي ظاهرة بكثرة أو بشدة هنا. والحد الثالث طبعا يعبر عن التيار المطرود من التفاعل. جميل. تعال نتأكد، نشوف هل هو سيصف هذا الأمر صحيح ولا لا.
So basically it's 2 steps of the derivation and then interpreting the result correctly. So that is an illustration of how powerful the path integral techniques are. You need to understand what the building blocks mean, but once you understand their meaning, you can immediately derive exactly valid or all order relationships between green functions and between Feynman diagrams. That is the power of the path integral. And let me just quote a few more detailed results without derivation. but just that you see how they can look like. For example, what you would like to do often is to have here a more detailed statement about this green function with all diagrams here. Because all diagrams can be distributed into one particle irreducible building blocks. So that would be equal to the following. All diagrams in the electron self-energy, all diagrams in the other electron self-energy, and then here all one particle irreducible building blocks, and then again all diagrams in the photon self-energy. So you can split up this building block that we have encountered into this more detailed version. That is an equality. And then of course you could derive similar Dyson-Schwinger equations for such an object, for such an object, and so on, and then you get a set of many such equations covering relationships between either full green functions or between one particle irreducible green functions and so on. So you can get lots of this, and you can do it also similarly for the electron.
أعتقد أن الطاقة الأولى لا تعتبر مطرودة من التفاعل. ربما يكون ليست مطرودة من التفاعل، لكن أنا ما أعرفه أنه عندما تعمل فورير ترانسفورم وتحول الدلتا إكس ولا إكس ناقص واي تحولها إلى مومنتوم يعبر عن الطاقة المطرودة من التفاعل. ربما أكون مخطئ، لكن النظرية صحيحة، وهكذا تفسر أفضل. يعني إذا اعتبرناها طاقة داخل التفاعل فهي متساوية لهذه الطاقات المطرودة من التفاعل، فهي كده صحيحة. لكن إذا اعتبرناها طاقة مطرودة من التفاعل اللي هو الحدي شمال علامة تساوي، إذا اعتبرناه طاقة مطرودة من التفاعل فهذا يمكن أن ننسبه إلى الطاقة داخل التفاعل، لأنه كلما زادت الطاقة داخل التفاعل زادت الطاقة المطرودة من التفاعل. ففي كل الأحوال هي صحيحة، لكن الدقة لأنه ينبني عليها اشتقاقات أخرى، على دقة أعتقد أنه يمثل. نحن طبعا قبل قليل شرحنا البروباجيتور، وشرحنا أنه البروباجيتور يجب أن يكون مقام أعلى من البسط، ويجب أن يكون يمثل البروباجيتور يمثل دالة جرين، بحيث أن دالة جرين تزيد. نعم هذه تعتبر طاقة داخل التفاعل، لأن دالة جرين تزيد مع الجاذبية. دالة جرين تزيد مع الجاذبية، وهذا ما شرحناه في الفيديو أمس عن أول فيديو الفائت الذي تحدث عن دالة جرين وأنها تمثل معادلة علي يوسف الطاقة. هذا الفيديو الفائت الذي كان قبل قليل. فالبروباجيتور يمثل هذه يمثل هذه الدالة، وبالتالي هذه المعادلة تخبرنا طاقة داخل التفاعل وطاقة مطرودة من التفاعل. نعم، طاقة داخل التفاعل وطاقة مطرودة من التفاعل، هكذا.
For example, for the electron self-energy, all diagrams for the electron self-energy, you could write a Dyson-Schwinger equation for this, which would look like the following. The tree-level electron self-energy plus the following. Here a tree-level building block, tree-level electron propagator from here to here, then a tree-level vertex from QED, then all photon self-energy diagrams, all electron self-energy diagrams, then they connect again with a one particle irreducible building block, and then it goes on with all diagrams for the electron self-energy. So then you see that if you combine it, you have several building blocks. Here all Feynman diagrams for the photon self-energy. For this we have a Dyson-Schwinger equation. Here all diagrams for the electron self-energy. For this we also have a Dyson-Schwinger equation. Here one particle irreducible building block, it is the same as here, and so on. So you get sets of equations. You can derive many more equations for all those building blocks, and in this way you can build up either perturbation theory if you want to, or you can build up set of equations which you might try to solve exactly by numerical methods, for example. And so these examples are also explained in a nice review which I want to point out to you. There is a review about this by Roberts and Williams. With the physics reports. And the archive number is this. And there in particular they look at exactly the same Dyson-Schwinger equations in their figure 2.1 and figure 2.2, so you can directly look at this, and then you see comments and derivations of exactly this. And as they explain, and as I mentioned already last time, one can use this also as one way to investigate QCD, for example. You do it for QCD, then you get non-perturbative identities which you might use to study the infrared behavior of QCD, the confinement behavior, and such non-perturbative properties.
بالنسبة للكيو سي دي النون برتبتيف من أين جاءت؟ طبعا نظريتي لازم تفسر هذا الأمر، لأن أنا نشرت كتاب أمس وقلت القوى المغناطيسية تمثل كيو سي دي، فيجب على نظريتي أن تمثل أو كتابي أن يحتوي على هذا الأمر. من أين جاءت النون برتبتيف؟ جاءت من الآتي. البرتبتيف أولا، البرتبتيف أو برتبيشن ثيوري يخبرنا عن الحد الأول ضخم، والحدود التالية هي حدود صغيرة، وبالتالي كأنما نحن نبتعد من المسبب هذا التفاعل، أي زيادة الإكس. طيب ماذا يحدث إذا نقصنا الإكس؟ تكون البرتبيشن ثيوري ماشية بالعكس من الحدود الصغيرة إلى الحدود الكبيرة، وهذا ما يحدث داخل البروتون. داخل البروتون موجود الكوارك. البروتون لديه كتلة 10⁻⁸ بالنسبة لمنظورنا نحن، وعندما نغوص داخل البروتون كتلته ستكون أكبر، يعني 10⁻10. هذه الكتلة مثل الكرة الأرضية، لنفترض أن الكرة الأرضية، هذه الكرة الأرضية عبارة عن كتلة ضخمة تمارس ضغط يسمى الوزن. طيب بعد ذلك أفرض أنك أحضرت صندوق من خشب. هذا الصندوق وضعته في الأرض، ثم جعلت فوقه وزن صغير. هذا الوزن الصغير ناتج من ماذا؟ ناتج من كتلة الأرض الذي يعطي وزن الصندوق، بالإضافة إلى هذا الوزن الصغير الناتج من تفاعله مع جاذبية الأرض. طيب أفرض أنك بدلت هذا الوزن الصغير بالوزن الأصغر، ماذا يفعل الصندوق؟ طبعا سيتأثر بطريقة أكبر. هذا التبديل بين الوزن الصغير والوزن الأصغر يمثل تماما أنك تنتقل في داخل البروتون من حدود سطح البروتون إلى حدود الكوارك، والكوارك تقع على بعد 10⁻18 والبروتون 10⁻16 والكوارك 10⁻18. وبالتالي هناك ضغط كبير يظهر، أو نقول تأثير كبير جدا يظهر للبروتون على الكوارك. طيب الكواركات تتفاعل مع بعضها البعض، هذا التفاعلات بمجالات مغناطيسية. لدينا تأثير البروتون، أيضا لدينا تأثير الكوارك مع بعضها البعض أيضا، لأن الكوارك عبارة عن كتل وجاذبية وعبارة عن شحنات لها سبين، وبالتالي هي أيضا تؤثر، وهي تضاف إضافة إلى تأثير البروتون. هذه هي ما تسمى بالنون بيرتبتيف، أن التأثير متصاعد، تأثير متصاعد، وهذا التأثير ناتج عن كتلة البروتون، ناتج عن كتلة الكوارك، ناتج عن الإسبين الناتج من هذه الكتلة. طبعا بالنسبة للفضاء ثنائي الأبعاد داخل البروتون، ما يفعله هو كالآتي: يعاني أولا الفضاء ثنائي الأبعاد يعاني من كتلة البروتون، طبعا كتلة عالية، ثم أضيفت إليها كتلة الكوارك. طيب ماذا سيفعل الفضاء ثنائي الأبعاد؟ سيفعل آلياته للدفاع لنفسه، آلياته كلها ابتداء من توسيع الفضاء مرورا بالسبين وطرد الطاقة، طرد الكتل، وهكذا. طيب إذا كانت كتلة البروتون زائد كتلة الكوارك لا تساوي، ليست بالقدر الكافي لفعل الفضاء ثنائي الأبعاد آليته. طيب ماذا يحدث في الفضاء ثنائي الأبعاد؟ طبعا نعرف أن الإسبين يزيد مع زيادة الكتلة، فالإسبين للكوارك يكون عالي، هذا الإسبين للكوارك يخلق مجال مغناطيسي، هذا المجال المغناطيسي يتفاعل أو يزيد بزيادة كتلة الكوارك، بالتالي نجد الكوارك التي كتلتها عالية يكون لديها مجالات مغناطيسية عالية، والكوارك التي لديها كتل خفيفة لديها مجالات مغناطيسية خفيفة. بالنسبة للفضاء ثنائي الأبعاد غير المتناظر، لن يحتمل كتلة البروتون أو النيوترون بالإضافة إلى كتلة كوارك عالي الكتلة، وبالإضافة إلى ذلك نجد أن هنالك مجال مغناطيسي عالي جدا، لهذا جعل كتلة البروتون يحتوى مباشرة بأقل الكواركات كتلة اللي هي الأب والداون. لكن لا أستطيع تفسير لماذا 3 كواركات، لأنه الحقيقة أنه بالنسبة للفضاء ثنائي الأبعاد 2 كوارك أفضل من 3 كواركات، لكن ال3 كواركات ربما لديها علاقة بال degrees of freedom بالنسبة للمجال المغناطيسي المتغير مع الأبعاد الطول عرض ارتفاع. فالطول عرض ارتفاع هذا المجال المغناطيسي هذه التغيرات تولد أو ترتبط ب3 كواركات، ربما يكون هذا الأمر. لكن هذه التفسير للكيو سي دي بحيث أنه تتضخم عند الأبعاد الصغيرة، تتضخم الكميات، وهذا واضح أنه الكميات التي تتضخم بسبب اللي هو معدلات التدفق العالية 10 أس ناقص 10، أقصد معدلات التدفق العالية اللي هي مقلوب الفترة الزمنية. معدلات التدفق العالية، هذه معدلات التدفق العالية تضخم أي شيء، وبالتضخيم هذا يعطينا النون بيرتبتيف ثيوري، وبالتالي نجد أن الأبعاد حساسة جدا، الأبعاد تجدها حساسة جدا لهذه معدلات التدفق للمكان والزمان، بحيث أنه كلما نقصت الأبعاد داخل البروتون كلما زادت هذه المعدلات بصيغة كبيرة جدا جدا، وهذه تصنف أيضا بالنون بيرتبتيف لأن الزيادة تكون كبيرة. نحن رأينا في كتابي أن البروتون على حدود 10 أس ناقص 20 أعطانا 10 أس 985. طبعا هي قيمة كبيرة جدا، الفضاء ثنائي الأبعاد يرفضها تماما، لهذا لن نجد كتل على 10 أس ناقص 20 إنما الكوارك أقل كتلة للكوارك أو مساحة أو حجم الكوارك هو في 10 سناقص 18 قل 19، لكن لا يمكن أن تصل إلى كوارك متواجد في 10 سناقص 20. فحجم الكوارك أكبر من 10 سناقص 20، حتى أن يعني هذه المعدلات التدفق لا تصل ما توصلنا إليه في الكتاب هي 10 أس 985 و 10 أس 984. هذه مستحيلة. فنجد أن معدلات التدفق العالية هذه تعطينا النون بيرتبتيف. فالنون بيرتبتيف للكيو سي دي قادمة من معدلات التدفق العالية. طيب ماذا عن الذرة؟ الذرة طبعا تتعامل بالبرتبيشن ثيوري. ماذا عن الذرة؟ الذرة لديها معدلات تدفق أيضا، لكن معدلات التدفق ليست عالية. لماذا؟ لأن الكتلة ضعيفة أو الطاقة الكهرومغناطيسية ضعيفة، بالإضافة للأبعاد كبيرة 10 سناقص 10. يعني اللي بالنسبة للبروتون 10 سناقص 16 اللي هو على سطح البروتون يدينا معدلات تدفق 10 أس 22. هذه بالنسبة ل10 سناقص 16. طيب ماذا عن 10 أس ناقص 10؟ بالتأكيد يدينا معدلات تدفق أقل من ذلك بكثير. لأنه الآر تكعيب فالآر تربيع فإن نقسم 22 على 2 هي 10 أس موجب 11. هذه معدلات التدفق التي يعطينا لها الذرة، وربما أقل من ذلك. طبعا تظهر في الإلكترون في طاقة حركية للإلكترون، وتظهر في طاقة حركية للإلكترون، وتظهر أيضا في شحنة الإلكترون. وبعد ذلك نرى المدارات متوسعة، حتى المدارات ذاتها متوسعة، هي 10 سناقص 10، لكن مع هذا هي متوسعة بحيث أنه مدار K ليس مثل مدار L ليس مثل مدار M وهكذا. نفس ما يطبق في QCD يطبق أيضا على الذرة اللي هي تسمى بالإلكترومagnetic فورسز، وتلك تسمى السترونج فورسز. نفس الفيزياء تطبق هنا وتطبق هنا، فقط الفرق بينهما هذه تطبق فيها البرتبيشن ثيوري لأنه كميات متناقصة، والكيو سي دي لا تطبق فيها البرتبيشن ثيوري لأنه تطبق فيها النون برتبيشن ثيوري لأنه كميات متزايدة، لكن نفس الفيزياء. وهذا ما يجعلنا نقول أن الديجريز اوف فريدم الزيادة التي لدى الكيو سي دي وخاصة بها اللي هي أحمر أخضر أزرق، هذه الديجريز اوف فريدم لا نحتاج إليها أبدا، فقط نعوض عليها بمشتقات المجال المغناطيسي بالنسبة للزمن وبالنسبة للمكان فقط، لا نحتاج إليها. ونفس هذا المجال المغناطيسي المشتق بالنسبة للزمن وبالنسبة للمكان يطبق أيضا على الذرة، ويطبق أيضا على الأرض، ويطبق أيضا على الثقب الأسود، ويطبق أيضا على النجم النيوتروني وهكذا. نفس المجال هذا نفس المعادلة تطبق، وبالتالي هذه المعادلة تخبرنا أن الفضاء متصل من الثقب الأسود من الأبعاد الكونية إلى الأبعاد دون الذرية، هذا الفضاء متصل، وأن المجال المغناطيسي هو متصل. فالفرق أين؟ في معدلات التدفق اللي هو المجال المغناطيسي مشتقة ثانية المجال المغناطيسي على المشتقة الأولى للزمن مضروبة في المشتقة الثانية الأولى للمكان. هذه معدلات التدفق هي ما تضخم المجال المغناطيسي. ولاحظ أن النجم النيوتروني لديه مجال مغناطيسي عالي، من أين جاء؟ بسبب هذه معدلات التدفق هذه. فالنجم النيوتروني لديه مجال مغناطيسي سبب هذه معدلات التدفق، لأنه بالقرب من الكتل فإن معدلات التدفق تكون عالية بالقرب من الكتل، وخارج بعيدة من الكتل يحصل التايم دايليشن ويكون معدلات التدفق قليلة. فالجاذبية تزيد هذه معدلات التدفق بالنسبة للملاحظ الداخلي، وبالنسبة للملاحظ الخارجي البعيد جدا يرى العكس تماما. وبما أننا نحن بعيدين من البروتون فإننا لا نرى هذه الخواص المغناطيسية، وإنما نرى أشياء تتعلق بالكتل، تغيرات تتعلق بالكتل، تفاعلات تتعلق بالكتل لا نستطيع فهمها، وبالتالي أطلقنا عليها أحمر أخضر أزرق، وهذه تمثل نوع من التفاعلات خاصة بالكيو سي دي. هي في الحقيقة ليست خاصة بالكيو سي دي، لكن احنا نعتبر ملاحظين خارجين لن نرى الخواص المغناطيسية الضخمة، لكن إذا أبعادنا قلت وذهبت داخل البروتون سنرى هذه الخواص المغناطيسية وسنراها ضخمة جدا جدا مثل ما نراها الآن نحن على النجوم النيوترونية والنجم المغناطيسي وهكذا.
So, let us come to our next topic, which is another way to derive similar exact identities between green functions, but this time connected with symmetries, and these are the so-called Ward identities. So let us discuss symmetries and Ward identities. And I will soon explain that the term Ward identities here is meant in a quite general sense. There are a few different terms like Slavnov-Taylor identities also, and their meaning is depending on the author, but let's see. So let us look at some field transformation. Phi I goes to phi I plus delta phi I, and in this case the action should be invariant. Okay. So that corresponds to a symmetry, and in the classical theory, if you have exactly this case, an infinitesimal variation which leaves invariant the action, you have a conserved current via the Noether theorem. So what is the fate of this conserved current and this conserved quantity in the quantum theory? So we assume again that our path integral measure is invariant, and then do our derivation. So we have here a path integral over the field variables of our theory, and let us again look at some green function phi 1 up to phi n times e to the I times the action. Then we do a variable transformation and use that the measure is invariant. So then the measure is invariant. We have the same d phi I of x, but here we have now phi 1 plus delta phi 1 and so on up to phi n plus delta phi n, and in the action we have e to the I times the same action because the action is invariant. So basically we have first done a variable substitution. All the phi's go to the transformed phi's, and then we use that the measure is invariant, that the action is invariant, but here the phi plus delta phi simply remains. And then we have an equality, a non-trivial equality between two path integral expressions. And since the variation of the field is by definition infinitesimal, we can only use this equality here at first order in the deltas. So let's use it at first order in the deltas. At first order in the deltas, this simply gives a sum of 1 delta phi each times all the other non-delta phi's. And here there is no first order term, therefore what we get is 0 is equal to the following path integral expression. Namely, we have here again a sum of L equal 1 to n, and then we have all the original fields, phi 1 and so on, but one of them is transformed to delta phi L plus all the remaining ones times e to the I times the action. Okay? So we have a sum, and in the summation each of the phi's here is once transformed into delta phi. And the sum of all those expressions gives 0. So what does it mean as an illustration on the operator level? On the operator level, this corresponds to the following equality between green functions. So we can write it as a sum sum over k, and then we have green functions involving all sorts of phi's. One of the phi's is replaced by delta phi L. All the other ones remain the original phi's. And this delta phi L, it might be a composite operator, it might be a product of phi's, it might contain a sum of different terms and so on. It might be a complicated expression. And so we have to take the expectation value of such a complicated maybe operator times normal field operators. And this sum of such green functions vanishes as a result of the symmetry of the action. So this is the reflection of the symmetry on the level of green functions. A symmetry identity for green functions, so-called word identity. Let's rewrite it a little bit more in two ways. One way is, let's say in quotation marks, I would call this in quotation marks delta of phi 1 up to phi n in quotation marks, because that is really an abbreviation for the line before it. It's the obvious thing. You see a green function with lots of operators, and applying delta to it in the sense of derivatives would generate naturally this expression. So in that sense I would use such a shorthand notation for the line above it. But also to make it super explicit, what does it really mean? What it really means is the following sum. Namely, first you have this green function delta phi 1 times phi 2 times phi n plus phi 1 times delta phi 2 and so on times phi n plus and so on up to plus phi 1 times delta phi n. So it's this sum of green functions that we are looking at. Okay, so this is the explicit form. That is the shorthand notation, and that is maybe a short, compact way to write this. So to summarize, in this sense, we get, using just the abbreviated form, delta of phi 1 to phi n vanishes for any symmetry transformation of the action, and this is called Watt or Slavnov-Taylor identities. And they correspond to a manifestation of the symmetry on the level of green functions. So this sort of thing is the analog to the Noether theorem on the level of green functions. Now, just a side comment on the name Watt or Slavnov-Taylor identities. Different people call things differently. What I always use is the following convention. I will use the term Watt identity in case this delta phi is a linear expression, and I will use the term Slavnov-Taylor identity if this delta phi is allowed to be nonlinear in the quantum fields. Why this distinction? Because if it is linear, then what do we have here? In case all the delta phi's are linear in other quantum fields, then what we have here is simply a linear combination of perfectly ordinary green functions. And each of them, just here you have some field operator, some field operator, some field operator. Therefore, this is just ordinary green functions of ordinary field operators. Some linear combination of them vanishes. However, if the delta phi's or some of them are nonlinear, then some of those green functions here are not ordinary green functions, but they are green functions of composite operators, which are something different, more complicated objects, and therefore the different name.
طبعا هذا ما أريد أن أقوله، أنه ماذا إذا كانت الجرين فانكشن الدلتا جرين فانكشن لا تساوي زيرو، وبالتالي الوارد ايدنتيتي تختلف. وهذا واضح في أن الوارد ايدنتيتي لديها كمثل بداية السلسلة أو في وسط السلسلة أو بداية السلسلة، عندما تم مناقشة الوارد ايدنتيتي اللي هو البي، عندما تضرب البي في السميشن اوف سميشن، او في تضرب البي اللي هو المومنتوم في الماتريكس تسمى الامبليتيود اوف انتراكشن ماتريكس، تعطينا زيرو. تم تفسير هذا الامر انه الماتريكس هذه تتكون من اثنين سالب وموجب، وبالتالي جمعهما سميشن جمعهما يساوي زيرو. يعني هي ليست ايدنتيتي خاصة بانه الماتريكس يساوي زيرو، لكن هناك الماتريكس هذه تنقسم الى قسمين، والقسمين متساويان. هذه لا تساوي هو من يعطي الزيرو، هو من يعطي الصفر. فاذا البارد ايدنتيتي تتعلق بالسميشن. طيب اللي هو الجمع. طيب إذا فرضنا أن هذه الماتريكس لا تتساوى، السالب لا يساوي الموجب، بالتالي هذه الوارد ايدنتيتي هذه لا تساوي زيرو. طيب متى لا تساوي السالب والموجب يتساويان؟ إذا كان طبعا السالب والموجب لها علاقة بالجيج فيكسين بالنسبة للفوتون، بحيث أنه الفوتون بولاريزيشن يعطينا اثنين حقيقيات واثنين ليست حقيقيات. الحقيقيات كان رمزنا لهم بالرموز 1 و 2. ليست حقيقية رمزنا لها بالاس والال، والاس يعطينا سكيلر وهذا مهم جدا، والال هو عبارة عن combination of اس 1 و 2. السكيلر هو الذي يلعب الدور، حتى ال تلعب دور، لأنه ال عندما نحللها تعطينا مباشرة فرميونات، اللي هو 1 و 2 عبارة عن فرميونات أو كتل حقيقية. الاس عبارة عن سكيلر، سكيلر يعطينا ماذا؟ يطبق معادلة كلاين جوردن، يعطينا كل ذلك. إذا الوارد ايدنتيتي لا تساوي زيرو في كخاصية أساسية، وإنما سميشن لها جمع بالنسبة طبعا هي الدلتا مضروبة في الماتريس أو في الجرين فانكشن، والتعبير الدقيق لها هنا أن هناك جمع، حيث أن الدلتا مضروبة في الجرين فانكشن أو في الفاي الأولى، ثم زائد الجرين فانكشن مضروبة في الفاي الثاني، ثم الفاي الثالث، وهكذا. هي عبارة عن جمع. فبالتالي نجد أن الحدود، هذه الحدود يمين علامة تساوي الحدود شمال علامة تساوي. طيب ماذا إذا حدث العكس، إنه لا تتساوى، فإن الوارد ايدنتيتي لا تعطينا الزيرو. وهذا ما يحدث عندما يكون هناك كسر في التناظر، عندما تكون الجرين فانكشن ليست نون انفاريانت، لما تكون متغيرة تحت تحويلات لورنس. لما يكون هناك كسر في التناظر فإن الوارد ايدنتيتي لن تكون صحيحة، لن تساوي صفر، وهذا ما يعطينا الاختلاف في الكتل.
Not everybody uses this naming convention, but it is our naming convention. So these are Ward and Slavnov-Taylor identities, and again I would like to derive an example for QED, which we already used in the last semester for the photon self-energy, where we said that the photon self-energy must be transverse. So contracting the photon self-energy with the momentum gives 0. And we actually didn't fully derive it, but we made use of it. But now we can derive it. And we do not only derive it for the case we looked at last semester, but we will derive it for all others in perturbation theory. So this is an example, word identity in QED. And then you will also see, not only will you see the derivation of it, but you will also see what I always claimed, namely the statement follows from gauge invariance, because now we will start by using gauge invariance as the transformation of the fields. The Lagrangian will be essentially gauge invariant, and then from this gauge invariance of the Lagrangian we will derive an identity which is the transversality of the photon self-energy. And then you will see that it is indeed gauge invariance which is the cause of it. But it is a little bit more complicated than the blueprint, because in the blueprint we assume that the action is invariant. In QED actually the action is not gauge invariant. Why not? Because we need the gauge fixing in order to quantize it, and so we will already have to go beyond this simple structure, but it will be possible to do it. So anyway, the QED Lagrangian contains now a gauge invariant piece plus a gauge fixing term. The gauge fixing term is minus 1 over 2 psi times d mu a mu squared. And this was already used in the Dyson-Schwinger equation, but we didn't talk about it because we didn't discuss gauge invariance. But this is part of this differential operator which gives rise to the photon propagator. So again, I write the same form as before. 1/2 a rho d rho sigma a sigma plus a rho j rho. Now we also need psi bar d psi. So that would be the free part of the electron, kinetic energy and the mass term for the electron with some differential operator curly d, which gives rise to the Dirac equation. So that is I d slash minus m. Then here we have the differential operator for the photon, which includes the gauge fixing. And here we have the interaction. So that is the QED Lagrangian. And the photon propagator between two photons with Lorentz indices mu nu has the name I times p tilde mu nu, which is the inverse of this differential operator. And let me now write here the full expression, 1 over p square plus I epsilon, and in the numerator we have minus I times g mu nu minus p mu over p square times 1 minus psi. Okay, so it's a kind of complicated expression for the photon propagator, but it arises completely directly from the inverse of that differential operator, including the psi dependence. Now, let us write down something else which is not needed in QED, but which is useful for us now. Namely, let us write a scalar field propagator. For a scalar field that we discussed in quantum field theory 1 extensively, we have also a propagator. Let me call it just p tilde without index, I times p tilde. And the scalar field propagator depends, of course, on the mass of the scalar field, m. Well, let's call it capital M. Capital M, which would be I divided by p square minus m square plus I epsilon. So, and of course, you see that the photon propagator contains here minus I divided by p square plus I epsilon. So this part of the photon photon propagator is the same as the scalar field propagator for m equals 0. So it's just the denominator p squared plus I epsilon. That is the same as for a scalar field. So therefore, let us note a relationship, namely what happens if you contract the photon propagator with p mu. And note that this is motivated because we want to derive the transversality of the photon self-energy, which also corresponds to contracting something with a momentum. So let's begin by contracting our photon propagator at 3 level with the momentum. So momentum p mu contracted with this p tilde mu nu. What is the result if you contract this entire expression? Let's also add the I. If you contract the entire expression with p mu, I give you 30 seconds of time to do the contraction. Okay, so a few terms drop out and cancel each other, and one term remains, namely, which terms drop out? If you look at a square bracket and contract with p mu, something drops out. Yep. Exactly. And what remains is only the psi-dependent term. So and that is systematic because this combination here is a transverse projection operator. G mu nu minus p mu over p square. This thing is a transverse projection operator. This is a projection operator in the sense of mathematics. If you square it, it gives itself back. And it is orthogonal to p mu, so if you contract with p, it gives 0. But the psi term remains, and the psi term is then minus times minus times minus minus I times psi times the p square drops out, and what remains is p mu over p square plus I epsilon. Okay, and this is now possible to express in terms of the scalar field propagator. Namely, here we really have minus I times psi times p nu times the scalar field propagator at mass equals 0. So that is a relationship for the 3-level photon propagator. Now our question is basically the analog of this for the full Green function, for the full photon Green function, including all higher orders. So the question is, what happens if you do p mu times all diagrams and that is the analog of the left hand side, just including higher orders. We know the result at 3 level and we want to know it at higher orders, and that is the momentum space question. The equivalent question in position space would be the derivative of the 2-point Green function a mu a nu. That is the same question in momentum and position space. Now, I already told you what we need to look at. The relationship follows from gauge invariance, and you also see that here the result at 3 level, you don't get 0, but you get something, and the something depends only on the gauge fixing term. So this corresponds to the non-gauge invariance of the action, and the gauge invariant part of the action here already gives 0. So we will use gauge invariance, and therefore let us also write down the gauge transformations. What are the gauge transformations of QED? So an infinitesimal gauge transformation of the photon field operator or photon field in classical electrodynamics is of course the derivative d mu of some function alpha. And then we also have some gauge transformation of the electron field, but let's not write it down, because anyway it is something and it makes the Lagrangian gauge invariant. But what happens to the full Lagrangian of QED? It is not invariant because of the gauge fixing term. It consists of a gauge invariant part, which is of course gauge invariant under the gauge transformation of the photon and the electron field, even though we do not care what the electron field actually looks like. But this is invariant, but the gauge fixing part is of course not invariant, and its non-invariance doesn't depend on the electron, but its non-invariance is simply now given by the following, plus minus 1 over 2 psi d mu a mu. And how does d mu a mu transform? It goes into itself plus D'Alembert alpha, and the whole thing squared, right? And so this is now not the same as before. So this is the same as the original QED Lagrangian, including the gauge fixing term, and then at linear order in the alpha we get the following shift, namely 1 over psi, the two cancels, d mu a mu times D'Alembert alpha. And then we have neglected higher powers in alpha. So this is the change of the Lagrangian. So the Lagrangian is not invariant under gauge transformations, but it transforms with this extra term. And therefore we cannot just copy the result from the upper blackboard, but we need to rederive it under the modified condition that the Lagrangian is not invariant, but the Lagrangian changes as well while we do a gauge transformation, and therefore the derivation is a little bit more complicated than at the upper blackboard, but the logic and the idea is exactly the same. So we will use the following: the path integral. We assume that the measure is invariant, and then we obtain 0 is equal to the following, namely path integral over all QED objects. And then we start again for the photon self-energy. We look at the following thing: photon plus its transformation times e to the I times the action plus its modification minus the original thing. Okay, so following the steps from above, you see the second line at the upper blackboard. You write down the left-hand side of an equation, then you do a variable transformation of the fields and the Lagrangian, you equate it, and then you subtract. And I immediately did that here, so I wrote down this expression, a mu times e to the I times the action. Then I transformed a to a plus delta a and L to L plus delta L. The measure is invariant, I subtract, and then I get this difference here, which must vanish. And the difference to above is that here we also have a delta L. And now we expand in first order in delta. Then we have a path integral over the following. So at first order we pull down the delta L, and one term with the a mu cancels, and what remains is the following. Namely, we have once delta a mu times, let's factor out e to the I times the original action, that can be factored out. And then once we have just delta a mu, and once we have a mu times delta n plus a mu times I integral delta n. These are the two terms. And both are then multiplied with e to the I times the original action, and the combination is 0. So what we have here is that 0 is equal to a sum of two terms. The sum of two terms. One term is just the delta L, delta A path integral, and one term is a more complicated object. So, okay, one step more, path integral. What is delta A mu? Literally, delta A mu is just a number. Delta A mu is just a number, namely the derivative d mu alpha at some space-time point x. So I suppressed here the space-time arguments, but it's at some space-time argument x. So this is just a number which can be pulled out of the path integral. So what we get from here is just this number itself times the usual normalization factor, namely the path integral over nothing. So, but here, what do we have here? Here we have a mu times the change of the action, which is this expression here. So let's write it down. I times a mu at the same space-time point x, then an integral over d4y times the change of the action, minus 1 over xi times d nu a nu and D'Alembert alpha. And the arguments are all y here, which is integrated over. Then this is a non-trivial path integral because it depends on two field operators a mu, a nu. So what this generates up to some numerical factors and derivatives, but what it generates is the two-point function for the photon. This is exactly the full photon Green function. It's exactly this expression, but modified with factors, minus 1 over xi times the derivative and times a number which can be pulled out of the path integral. So how can we simplify the whole thing in order to obtain the nicest form of an equation? Well, in the following way. One thing that you can do is to choose alpha of x as a special function. Namely, you know, we have here a multiplication with D'Alembert alpha, but what we really want is the Green function. So it would be nice if the D'Alembert alpha would just not be there. We can make it vanish by saying that we choose alpha in such a way that D'Alembert alpha gives a delta function. If D'Alembert alpha is a delta function, then the integral collapses. The D'Alembert alpha and the integral together give just a nu at some space-time point. How can we do it? By choosing alpha such that it is the Green function of the D'Alembert operator. But what is the Green function of the D'Alembert operator? It is, of course, the scalar field propagator by construction. So we choose alpha of x as the scalar field propagator, such that D'Alembert alpha of y is equal to a delta function of x minus y. Okay, and that means that alpha of y is nothing but the scalar field propagator p times minus 1 at mass 0 of x minus y. Then this is valid by construction of the scalar field propagator. Okay. So that is of course a trick, but it simplifies the whole thing. And okay, maybe the okay, a question. Good. We don't know it, we assume it. That is the point of the entire section. the entire section always assumes that the path integral measure is invariant, and under this assumption we derive various interesting things, and then once you have a concrete path integral definition, you can check whether this assumption is true. If it is true, all of our statements are immediately valid. And we will later discuss one example where this is the case. And last time we also mentioned already here that there are examples where it is not the case. For example, there are cases in the Fujikawa discussion of anomalies where the path integral measure is not invariant under certain symmetry transformations, and then symmetry derivation doesn't work, and this corresponds to a symmetry breaking by quantum effects. But these are all special cases, but we work here under the assumption that the measure is invariant. Okay, so now let's plug it in. In principle, we are already done. We now have to look closely at what we have. If we plug in this expression, the D'Alembert alpha gives rise to a delta function between, let's say, or let's maybe put z minus y, gives rise to a delta function, and the integral collapses, and what remains is simply a nu at the position z times the psi-dependent prefactor. And here we of course then also have the normal derivative of this scalar field propagator, and then we can multiply with the inverse propagator if we want, or we don't even have to do it. We can immediately, actually we do not have to divide by anything. We immediately can look at the operator correspondence of this equation, and then we have here from the first term minus derivative of the scalar field propagator at zero mass of x minus z, and the second term is minus I divided by xi times the full photon Green function a mu of x and d nu a nu of z. That's immediately it. And if we go to momentum space, that is the desired equation. In momentum space, I times a derivative gives of course the incoming momentum into the appropriate field operator, and then we can translate this into the equation above. So then we have here, we can bring this to the left hand side, then that times minus I gives us the contraction with the momentum that gives exactly this left hand side, including the momentum contraction, but in this case contracted with p nu. P nu contracted with a photon 2-point function, and on the right hand side we have this. Okay, so let's write it down. 1 over xi from here times p nu times the full photon 2-point function from here is equal to this thing here. In momentum space this becomes p tilde, which is the scalar field propagator, which is then p I p mu divided by p square plus I epsilon. And that thing here, the scalar field propagator multiplied by p mu, we have derived it already up to the factor xi. This is the same as the contraction of the 3-level photon propagator with the momentum. So this is equal to 1 over xi times p nu times the 3-level photon propagator. And then we have our desired equation. We could cancel the 1 over xi on the left hand and right hand side of the equation, but what we get is the contraction with p nu of the full photon 2-point function is equal to the same thing at tree level. In other words, the contribution of all higher orders to this is exactly 0. All higher orders satisfy p nu contracted with this is 0. The only non-zero contribution is tree level. So tree level is exact in this equation. So let's write it down. P nu times all higher orders is 0. And then in particular, this implies what we have used in the last semester. P nu times sigma mu nu of P is 0, where sigma mu nu is the one particle irreducible building block for this, as we have defined it in the last semester. Okay, so this is
هذا طبعا ما كنت أقصده في الشرح قبل قليل، أن بي ميو في السيجما يساوي 0، وهذه السيجما عبارة عن الجمع، وهذا الجمع ظهر هنا اللي هو ابتداء من 1 على صايب في بي نيو في أول هاير دياجرامز يساوي هذا، يساوي التري ليفل اللي هو بي نيو 1 على صايب بي نيو في التري ليفل يساوي 0. طيب ماذا يحدث إذا كانت لا تساوي 0؟ هذا ما شرحته قبل قليل. ماذا يحدث إذا كان لا تساوي 0؟ فهذا يعني أن الهاير دياجرامز كلها الهاير ليفلز لا تساوي 0، يعني الدياجرامز ما ممكن يحصل له كونتراكتد لما يسمى بالإيريديوسبل دياجرام. هذا الأمر يمكن تحقيقه من أين؟ من هنا. عندما افترضنا على دالنبير بالنسبة للألفا يساوي دلتا. افترض العكس، فقط افترض العكس، أنه دالنبير بالنسبة للألفا لا يساوي دلتا فقط. لماذا؟ لأنه ألفا تتغير من في التفاعل من داخل التفاعل إلى خارج التفاعل، لا يمكن أن تساوي دلتا، لا يمكن أن تكون ثابتة. إذا فرضنا ذلك من هنا سنتوصل إلى هذه المعادلة أنها لا تساوي 0، بالتالي الايدنتيتي وارد ايدنتيتي لا تعطينا 0. وهذا يعني ماذا؟ هذا يعني أن هنالك تغير في التفاعلات، وهذا واضح من نظريتي أن معادلات تدفق الزمان والمكان يتغير في التفاعل من وسط التفاعل لطرف التفاعل، فبالتالي وارد ايدنتيتي لا تساوي 0. وهذا واضح في ما ذكرته قبل قليل عن البولاريزيشن الاس والال. ال عبارة عن كومبينيشنز والاس يبدينا سكيلر، فهذه لا يتساويان مع بعضهم البعض، وبالتالي لا تعطينا 0.
result. And this has used in quantum field theory 1b section 4. So section 5.1.3. Alright, so this is how you can derive water identities in QED, and of course you could go on deriving similar equations for more complicated green functions. It might get a little bit more involved, but you can do it. You can in particular do it in basically the identical way for green functions with many more photon operators. If you have only many more photon operators, then the same logic is fully valid. If you want to know what identities for green functions involving electron fields, then you have to plug in also the gauge transformation of the electron, and the result will contain additional structures. but the derivation can always be done in this way. And here in particular we have derived this important point, namely the transversality of the photon self-energy, in other words the transversality of all higher order corrections to the photon propagator. This is very important. And you see also this more general thing. What will always happen in the derivation of these water identities is that you start from a gauge transformation of the photon, which contains this derivative, such a longitudinal term in momentum space. And therefore the water identity will always lead to this operator here, d mu a mu, because that comes from delta L. And so therefore the water identity will always give you some relationship of something with the contraction of a photon field. Any water identity will always contain something like this. In momentum space, all water identities contain the momentum contracted with an external photon line and then some other structures of green functions. But this operation here will always be a part of those water identities, and that simply comes from the gauge transformations. Okay, any questions to this? So this would end our examples, but now we would come to the opposite direction, as we just announced. Namely, I want to show you an example where the measure is invariant, where we have an explicit definition of the path integral measure, which turns out to be invariant. And then under that condition, all of what I say here is exactly true. And the example is the so-called dimensional regularization, where we go away from 4 dimensions to d dimensions, and where we regularize divergences appearing in the calculations in d dimensions. And if you regard the path integral as effectively defined via Feynman diagrams in d dimensions, then the measure effectively defined in that way is invariant under any infinitesimal symmetry transformation. And so we will prove it. And after we have proved it, you then know that this box here, for example, is valid automatically in d dimensions in the regularized theory at all orders. And then that completes the proof that in dimensional regularization, the photon self-energy is transverse at all orders of perturbation theory. It's a full proof. So let's do that. Okay, so what we need to do now is something that has another name, namely the regularized quantum action principle. In dimensional regularization. And this is just a different name for exactly the statement that I described. And let me also refer here to our review, where you can find more information about that. Section 4. So the statement is the following. First of all, dimensional regularization effectively defines a path integral measure but only perturbatively. So it defines the path integral in terms of Feynman diagrams, and in this way it also defines a path integral measure, of course, with certain properties which are defined by the dimensionally regularized Feynman diagrams via dimensionally regularized Feynman diagrams. So as a formula, we might write d phi of some functional of fields times e to the I times the action. We define it now in the following way. The action, or the Lagrangian L, is defined in d dimensions, and it's integrated over in d-dimensional space-time, where d is of course not an integer number, but it's a continuous variable, and this is meant in a formal sense defined in terms of regularized Feynman diagrams. So the definition of this path integral is given in terms of green functions. So this is given in terms of regularized Feynman diagrams. In the unequal to 4. And that automatically also implies that all divergences which might appear in the calculation of Feynman diagrams, they are treated in dimensional regularization, so the result might contain 1 over d minus 4 poles. So we cannot maybe immediately take the limit d converging to 4, but for d unequal to 4, this is completely well defined, and that gives an implicit definition of the path integral. If we use that as a definition of the path integral, then the measure is always invariant. So this would be the loose statement that you can do, and what it means technically is the following equation, that we have 0 is equal to the following path integral of the thing that you would obtain by doing the naive path integral manipulation from before, namely factoring out e to the I times the action in d dimensions. You get two variations. Once you get the variation delta f of this functional here in the beginning at first order in all the field variations, plus you get the same functional times the variation of the action delta L in d dimensions. These are the two terms that you get, and the path integral over this combination vanishes when you define the path integral just via Feynman diagrams. So, and again, the variations are the terms linear in the infinitesimal field variations delta phi. So this is one way how you can express the statement in dimensional regularization. Very simple statement, but very powerful, obviously, because it includes all the derivations and all the relationships that we have derived before. Okay, and so this is now defined to mean a relationship between Feynman diagrams in d dimensions. That is what it means. But it is an all-order statement. So maybe we do not quite have enough time to prove it completely in the remaining 5 minutes. But let's make a few comments. So first of all, that means that all what we have said before is valid in dimensional regularization. In particular, we know that in QED the photon self-energy regularized in dimensional regularization is transverse it at all orders. For QED, which is of course an extremely important and powerful statement.
طيب هنا أريد أن أقول شيئا، وهو أن ذكرنا قبل قليل أن لا باث انتجرال not invariance، يعني هو not invariance non invariance under d dimension. وذكرنا أن الدي دايمنشن يعني أن التغير في الدي ما زال مستمرا يعطينا تغير في الكتلة. لا 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 regularization هذا عكسا تماما لما ذكرته، لأنه يحاول أن يجعل الدي صغيرة، اللي هو التغير في الدي تكون صغيرة كما سنرى في الفيديو القادم. سيجعلها صغيرة، بالتالي أي تغير في الدي تكون صغيرة حتى تستطيع أن نطبق البرتبيشن ثيوري. وفي هذه اللحظة أنه نجعل الحدود التي تكون أعلى هي حدود صغيرة، بالتالي يحصل regularization اللي هو كما يقال الدي regularization، يعني كما نقول استقرار، شيء من هذا القبيل، لأنه المفترض أن يكون جميع التفاعلات تحصل عند أبعاد واحدة. 4 dimension يعني 4 dimension، إذا تغيرت الأبعاد يعني تغيرت الكتلة. فهذا ما يقصد بهذا الموضوع.
Do you have any question? Otherwise we might start with the proof. The proof is actually fairly simple, but I think 2 minutes are not quite enough. So let me
حتى انظر هنا يحصل إذا ضربنا البي ميو في السيجما يعطينا زيرو، اللي هو الايدنتيتي الوارد ايدنتيتي عندما تكون الأبعاد ثابتة. طبعا الأبعاد ثابتة يعني كتلة ثابتة، أبعاد ثابتة كتلة ثابتة، أبعاد تغيرت الكتلة تغيرت. يعني هذا أيضا يتفق مع نظريته ويفسرها مباشرة. الوارد ايدنتيتي يكون صحيحا، حيث أن ضرب البي ميو في السيجما يعطينا زيرو. السيلف انرجي للفوتون مثلا يعطينا زيرو في حالة انه الابعاد تكون ثابتة، لكن في وسط التفاعل ليست ثابتة، الكتلة ليست ثابتة، فالكتلة ليست ثابتة. يحاول الفضاء صناعة الابعاد ان يثبتها، لكن هي ليست ثابتة، لانه عند الابعاد الصغيرة الطاقة تكون عالية جدا، وبالتالي يقللها الفضاء صناعة الابعاد، يحاول ان يقللها، وهي بنفسها تقل كلما ابتعدت عن وسط التفاعل هذه الطاقة، وكأنما الأبعاد تتغير، لكن هي لا تتغير، لكن الطاقة تتغير، بالتالي الكتلة تتغير، وتغير الكتلة يمكن أن تفسر بمعنى تغير الأبعاد.
The idea of the proof is the following. It is very similar to the details of the derivations that we have done before, where we have to write down the Lagrangian in terms of the free Lagrangian with the differential operator and the interaction Lagrangian, and the differential operator that appears in the free part defines the free propagator. The free propagator is a part of the Feynman diagrams, also in dimensional regularization. And using this property, that the propagator in Feynman diagrams is the inverse of the differential operator which appears here, that is basically the core of the proof. And so then this will give rise to relationships between the regularized Feynman diagrams, and we will identify Feynman diagrams here in this building block and Feynman diagrams in that building blocks, and we will see that the diagrams are the same because they are derived from the same Feynman rules. Therefore the diagrams are the same, and this sameness comes from this relationship for the d-dimensional propagator. So the core of the proof is really this thing, that also in d dimensions this differential operator and the propagators in the regularized Feynman diagrams, they are the inverses of each other. And that is actually a non-trivial property of dimensional regularization, and it is an important property of dimensional regularization that you can write, let's say, the propagator of the electron, even in d dimensions. You would write it as 1 I divided by p slash minus m, where this p slash is now a d-dimensional p slash, such that this propagator is really the inverse of the differential operator which appears in the d-dimensional Lagrangian, where you would have I d slash minus m, and the d slash is also interpreted in d dimensions. So there is this relationship between the propagators in regularized Feynman diagrams and the differential operators in the regularized Lagrangians, and this is the core which enables this property to be valid. And you can easily imagine regularizations where this is not true, where you simply treat the Lagrangian differently from the regularized Feynman diagrams. For example, there are things like momentum cut-off regularizations where you do not do this, but you cut off the integration at some high momenta and so on, and then these properties might not be valid in such regularizations. But in dimensional regularization you have this simple property which looks not very deep, but it's the core of this derivation. And so once we will write down the diagrams corresponding to this and to this, you will see the identification, and the proof follows fairly easily. Okay, then we will do that in the afternoon. See you then.